Okay, so welcome everybody. In today's lecture, I will be talking about context unification, which is a generalization of the previous problem of word equations. However, hopefully the algorithm is standalone, so while previous knowledge is somehow welcome, then you should be able to follow the argument even without the previous, well, the knowledge of the previous algorithm for the word equations. Okay, so what is the context unification? So you probably have heard about first order unification. So in this problem, well, instance of this problem can look like that you are given a term with some variables, f on x, say a, if equals f on b, y, and you are supposed to tell whether this equation is satisfiable or not, and both this x and the y stand for some terms, and then it's by some easy decomposition of the terms, we can see that x is equal to b and y is equal to a, and in general this decomposition method works, and in p time, actually in linear time, we can find a unifier, we can find a solution of such an equation. But here the x and the y, they both represent terms. Okay, so well-defined closed terms. I will make it more precise what a term is later on, but probably everybody knows what a term is. In the second order unification is a more general problem in which a variable can take some arguments. So you can take arguments like terms t1, t2, t3, and those are, well, the arguments are terms. And then the substitution for x is some sort of a tree, and it has some designated nodes. This is node number 1, this is node number 2, this is again node number 1, this is node number 3. So it can use those arguments perhaps many times. So when you apply, this is what is substituted for x. And then when you apply it on terms t1, t2, t3, then this node numbered with 1 is replaced with t1. This is also replaced with t1, this is replaced with t2, and this is replaced with t3. Maybe as an instance of this problem, when we have something of the form x on f on c, c equals x on equals f on x on c, x on c, then it's not so difficult to show that every solution is of the form that x is equal to some full binary tree of some height, which has f in the middle, and only c's and those empty, well, the nodes labeled with this argument 1 in the beginning, and then both the left-hand side and the right-hand side will evaluate to a full binary tree, which has all the inner nodes equal to f and the bottom nodes and all the leaves labeled with c. So in particular, there is no upper bound on the number of how much this argument, on the number of times this argument is actually used in the second order unification. But here the problem is that as this was in P, this problem is undecidable. And some very easy variants in which you allow only one variable, one argument to this variable, and so on. And the main problem is that this bound, so we do not know how many times the argument is used, and this number of times it's used actually simulates some computation. Okay, there are different proofs why it's undecidable, but this unbounded number of time of usage is the main source of undecidability. So the context unification is one of the problems which is in between those two, and judging from your perspective, it might be described as the problem in between. And it is a generalization of word equations. If you do not know what it is, then it doesn't matter. So the idea is similar as in the second order unification. So your terms take arguments. Without loss of generality, it can be one. So it doesn't really matter that whether there is one argument on several. But the thing is that when you take the substitution, then you can use this argument exactly once. Okay, so you can use it once, and you have to use it exactly once. So using this previous example, when we have x on f c, c equals f on x on c, x on c, then the only substitution that we can actually make is that x is equal to this argument. So it just takes the argument and returns exactly the same. And then both sides evaluate to f on cc, because we know from this previous discussion that all other solutions are actually of the form that they use this argument a larger number of times, and this is not forbidden, so we can use this argument exactly once. Okay, so in particular, if we are allowed only letters of, well, all our nodes are supposed to have arity1, then the tree that we can look at is just a vertical tree which has some designated leaf at the very bottom, and this, when you rotate it by 90 degrees, then those letters A, B, C, D, E, well, maybe C is not the best here, constant. When you rotate it, then this is A, B, C, D, E, and a constant at the end. This constant can be removed because it has to be there anyway. So this can be viewed as a word. So therefore, context signification generalizes the word equations. And this problem was defined somewhere in the late 90s, and initially it was not considered as a generalization of word equations. Well, it was observed that this is a generalization of word equations, but the real reason why it was defined was different. So on one hand, it was somehow used as a formalism in some learning of natural languages. It was also a generalization of different types of constraints that you can have in some term rewriting. And there was also some other motivation. So not just the fact that this was a natural generalization of word equations. And initially it was, so the previous algorithm, it was not known whether it is decidable or not to verify whether you can solve such equations well, whether you can solve equations for context signification. So the reason is, on one hand, when we looked at the proof of undecidability for second order unification, so those proofs essentially use the fact that arguments are used many times. So it simply does not generalize to this case, because here we can use the argument only once. And on the other hand, all the known proofs for word equations which were at that time, so one of them was the proof of Makanin, and the other proof was by Plandowski, they essentially used some rather complex factorizations of words. So for Plandowski, there was also some compression involved, but nevertheless, he used some complex factorization of words. And when you have a complex factorization of word and you try to apply it on terms, then it might be that your factorization becomes just too complex to be actually used. And well, this was the main problem. So the tools for strings which were used in terms of word equations, then no longer worked for terms. Okay, and today I will show you the well, piece-based algorithm for the context signification, which is hopefully reasonably understandable. Okay, so let us define the setting that we have. So we are working with terms or with trees, as you would, well, both views are allowed. So the tree is labeled. So there are some, there is a so-called signature, so alphabet or signature. I have problems with alphabet or signature. So this is some sort of finite set of symbols that we can use to label the nodes of the tree. And we have the arity. So each symbol has an arity. So say C is a constant, so it will have arity 0, and I don't know, F is a binary symbol, so it will have arity 2. So in particular, we assume that every letter has a fixed arity, although we could use it for different arities and just have different copies and somehow mark them that this is a different copy which has a different arity. So this assumption is not crucial. Okay, the trees that we are looking for that we are considering are rooted. So there is a designated node, which is the root node. They are ordered in the sense that we know what is the order on the children. So this is the first child, the second child, and the third child. So the say F on AB is different than F on BA, because here the order on the children is different. And they are well formed, so well formed as terms, meaning that if arity of F is K, then F, well, node with F has K children. So that the arity, which is this, well, this arity function is the arity that we are using on the trees. So if it says that f has arity 3, then it has 3 children. Okay, so this is exactly the definition of terms, and if you want to think that those are trees, then okay, but we need to satisfy those conditions as well. So I will also sometimes write things as trees to make it more clear as a description, but also sometimes write them as terms, because then sometimes it's easier to define things precisely. Okay, so now, as I said, the variables should represent something more complex than a term, so they should represent a term with a missing parameter, and those terms with missing parameters will be also used somewhere else in the compression that we are going to use. So we also would like to define it. So the parameters are just some special, we will treat parameters as some special symbols. I'll mark them with larger dots. This one is without dot, and otherwise we have some parameters which are, well, dots with some indices, index 1, index 2, and so on. So those will be the parameters. And the pattern is a term over the sigma, which is the alphabet from the, well, signature from the previous part. Let those parameters be p, together with the set of those parameters, and we extend the arity such that the arity of each parameter treated as a symbol in this term is 1. Okay, so every parameter has arity 1. So we build terms over those symbols from the signature plus the parameters which have, sorry, not 1, 0. 0. Meaning that all of them have to be leaves. And it's linear, meaning that each parameter can be used at most once. Used at most once, which corresponds with this previous discussion that, well, the variables can use the argument at most once. Okay, so this is a pattern. So for instance, a pattern would be f on a dot on, and this, well, this is the first parameter. This is, well, maybe this would be more useful. This is the first parameter. This would be the second parameter. And if we were to make those parameters the same, then this is not legal, okay, because we use the same parameter twice. So we need 2 different parameters if we want to make it a pattern. Okay, this means a linear pattern. So for the occurrence of the pattern, so if we have some term, then we say that a pattern occurs somewhere if, well, this is a subtree which can be obtained by, well, removing some upper part and removing some subtrees. And for each subtree which we deleted, well, we put a node with this parameter. So for instance, if we had something like this, f a b, then the pattern f a dot occurs here. It occurs here. And maybe also this one, this would be a. And on the other hand, the pattern f a star, it occurs here. And it occurs here. We could also make patterns which are larger, like f, and they have three missing arguments, sigma 1, sigma dot 1, dot 1, dot 3, and then the only occurrence of this pattern would be here. Okay, it could also be that one letter has many missing arguments. If this is sigma 1 and 2, then those have 3 occurrences here, here, and here. Okay, so those are occurrences of a pattern. And then if we are giving a term or a pattern, then the sub pattern is just a pattern which occurs in this one. So all of those which I listed are sub pattern of this term, but for instance, anything with G which does not occur there is not a sub pattern. Okay, and we know how to turn a term into a pattern, so we need to delete some parts and replace them with the arguments. But on the other hand, we can well, we can turn a pattern into a true term by substituting something for the arguments. So if we have a pattern, then by something like this, this should be in the other direction. So this denotes a pattern in which I substitute the term t1 for this first argument and t2 for the second argument, and in general I could substitute an arbitrary number of arguments, and some of those could be left in place. So I do not need to instantiate all the parameters at once. Perhaps I can instantiate the first and the third and so on, and also I do not need to instantiate with the term. I could do it with a pattern, and in the end I would still get a pattern. Okay, and this is done by just replacing this symbol by appropriate term. So for instance, if we have a pattern f on dot 1 dot 2, then if I take f on dot 2, I'm always writing this in the wrong direction, with a, then this is the pattern f on dot 1 f on a. Okay, I wrote that those dots are, well, could be something without a number, or the parameters are numbered, but since each of them occurs only once, then I will not deal with some problems that we substitute the first one or the second one, so there is some order of those arguments is not so nice because the second one is missing and so on. It's important just to know that there are parameters, their names actually does not matter until you instantiate, and then it should be some more or less, it should be clear from the context what is substituted for what anyway. Okay, so the names of those parameters are needed for formality, but we'll not deal with them so much later on. Okay, so now we can state our problem. So for the context unification, this is a decision problem. And again, usually when we are giving a decision problem, we can, we can also not only provide a yes/no answer, but actually a solution, but nevertheless, we view it as a decision problem. So on the input, we are giving a signature with the arity. So the function which tells you what is the arity of every letter. We get some sets of context variables. So those are variables, I will denote them with capital letters X, Y, Z. And the idea is that we should substitute patterns for them. Okay, I didn't tell it previously. So the pattern with k arguments is called k pattern. Okay, so we want to substitute one patterns for those variables. There are also some term variables. I should use some different letter, maybe X prime. And I will denote them with small letters. And for them, we want to substitute terms. They are not so much, we could do without them, so we could simulate it using context variables, but it's easier to talk. From time to time, it's easier to describe if we also allow term variables. And the problem is given as a context equation. So we are given an equation of two terms, u equals v, and this u is a term, well, built over sigma, term variables, and context variables and term variables. Those variables, they should be called pattern variables in our terminology, but for historical reasons, they are called context variables. We treat them as symbols of arity1, and those term variables as symbols of arity0, which is consistent with the fact that what we want to substitute for x is just a pattern of arity, is a one pattern, and what we want to substitute for a term variable is just the term, so it's a well-formed term, it doesn't take any arguments. And we are asking whether, is there a solution? Is there a solution? So what is a solution? So in general, we want a substitution, and the substitution is maybe S. Substitution for term variables, we return one patterns, and for pattern variables, we return one patterns. For terms, term variables, we return terms. over sigma, and we extend it in the natural way. So if we want to we extend it to patterns in general in a natural way. So if we apply it on f on some term 1 up to term k, then this is just f on s on t1 up to term k. And so we know how it is on the variables. The only important part is that when we apply it s on a term variable or on a pattern on the context variable on the term t, then what we want to do is to take s on x, and this is a one pattern, and then for this unique argument which is missing, we substitute as well the term which is computed below. And of course, a solution is just a substitution such that this s on u is s on v. So maybe as a simple example, when we are giving a very simple equation, x on c equals x on c prime, and our signature is f, which is binary, and c prime, which are both constants, then not x, for x it wouldn't work. Why? Then one of the solutions is of the form that x is equal to f on dot c prime, and y is equal to f on c dot, and then x on c is just f on c prime, because we substituted this part by c, and y on c prime is the same as f on, well, again, f on c prime. Well, this has to be like that. Okay, if we had something more, even more trivial, like x on x equals y on x, where this second x is just a small one, then essentially everything here would be a solution. So we take x just to be any pattern, and small x to be n equal to y, and small x to be any term. Then this equation is trivially satisfied. But we could also have some different solutions, like that x is f on dot and some term, y is f, but it just switches the argument. So it's then on the end, the argument, well, the argument is the second child, and then we need to substitute the small variable with term t. Okay. But anyway, this idea that what we do with this special symbol is that we just replace it with the argument, which is the argument of the variable. Okay, any questions at this point? So how does the semantics of the equation and the solution works? Okay, so for now, notice that even in this trivial example here, we needed this symbol f, this binary symbol f, to actually have a solution. And it's easy to see that if we have no symbol of arity at least 2, so if f would be of arity 1, then this does not have a solution, because this unique constant, which has to be somewhere on the end, here is c and here it is c prime. So we need to somehow switch them. So we need to, the terms need to, at some point there need to be at least 2 arguments for some of the function symbols available. Okay, so it's not true that we can use only the symbols which are visible in the equation. So here we need to use this binary symbol, and if this binary symbol were not present, then we couldn't, well, symbol of arity at least 2 were not present, then this equation would not be satisfiable. Okay, so the signature somehow matters. But I would like to say that this is the only reason, the only moment in which it matters. So that perhaps we need to add some binary symbol, and later on I would like us to forget about the signature. Just look at the letters which are in the equation and say that this is fine. Okay, and why it is that? So there is a couple of simple observations. So first of all, if sigma has no constant, then this is trivially, there is no solution, because we simply cannot do any terms. Okay, if there are only symbols of arity 0 and 1, then this is equivalent to word equations, because when we well, we can use only, if we have any equation, then we can just write it as a word equation and replace every variable, well, every context variable with a word variable, and every symbol, function symbol A with a letter A. And at the very end, the only difference could be that there is this term this term variable, but we know that it's actually a context variable applied on some function, on some constant C. There is a unique place where this constant C is present, so we can just choose what's the ending constant. And the same happens on the other side. So we can just replace symbol by symbol and obtain a word equation. And we already know that this is in P space, so there's no reason to treat it as a word equation. Of course, it could be that this is not satisfiable because we somehow force that there are different constants at the end of the terms, and then it's trivially not satisfiable. So either it's not satisfiable at all, or it trivially reduces to word equations. Okay, but this is just a simple, a very simple argument. But what's more important is that, assuming that those trivial situation does not hold, so our input signature has a constant and it has a letter of arity, at least one, then we can add to the input signature a binary letter without affecting satisfiability, and a unary letter. Okay, the binary is more important, but the unary. So we can assume without loss of generality that our sigma has a binary and a unary letter. And why it is that? So okay, so suppose that somewhere in the equation, so those unary and binary symbols are not used in the, so in this direction. So so suppose that we use some letter A or some letter F, which are not used in the equation at all. Okay, so then all those occurrences of those letters need to be in the variables. So in the substitution for the variables, because they are not in the equation. Okay, so we could, if we have this chosen symbol G, which is of arity greater than 2, and we have this chosen constant C, then we can replace every A with G, well, which at first position has nothing, and all other positions has this fixed constant C, and then it can, well, this effectively simulates a unary symbol, and we can replace every A with this symbol, so all of the occurrences are changed exactly the same way. And the same for F. So whatever the F is binary, so we F is just replaced with G, such that it takes the first 2 arguments, and all next arguments it just takes the constant C. Okay, and in the other direction, okay, so if we do not have a solution, if we have a solution without those 2 constants, then of course we also have a solution with those 2 constants. So in the other direction is trivial. Okay, so yeah, if we had a solution, then we still have a solution. Okay, so this is done. And secondly, we can also remove the letters from the signature. Okay, so we do not, if there are many letters, say they do not would not occur in the equation, then we can remove them, well, assuming that we leave something behind. So we leave a symbol of arity 2, and we leave a unary symbol and a constant one. This unary symbol is not really needed, but just for the sake of the later argument. So we preserve those symbols of 3 different arities. Okay, and the argument is essentially the same as here. It just goes the other direction. So if something is, so suppose that we use some letter F, which is of some very large arity, and it's not in the equation, then we can replace it with this our chosen binary symbol B by just, let's say if it has 4 arguments, then we simulate it with such a tree which is built using B. Okay, and well, that's in one direction, and in the other is clear. So if we have a solution of a smaller signature, then we also have a solution over the larger signature. Okay, so later on we can assume, so for the remaining of the proof, we just fixed some constants. We fixed some symbols of RET2, RET1, and RET0. So let them be F, A, and C. And we always assume that the signature of the equation which we see is consists of letters that we can see in the equation plus those FAC, which are from the original signature. Those are those unary, binary, unary, and the constant. Okay, and this will be called a trimmed signature. So if we have an equation, then the trimmed signature is just the signature of letters which is in the equation plus those three constants, those three symbols. Okay, so the main idea of the solution is that we are going to replace some sub patterns of the equation of the solution by some smaller ones. Okay, so we define some sub patterns which we later describe how to compress. So the first type of pattern I will call it a chain. So a chain is simply a sequence of unary nodes, perhaps different ones, but still of unary nodes. Okay, so this is A, there's again B, and so on, and at the end there is, well, this is still a unary one. Okay, so a sequence of unary nodes. This is a chain. A maximal chains means that, well, we cannot extend it to the below or higher. A pair is a chain AB. Well, and A is different than B. Usually we will assume it. Okay, so a simple chain of that. An A chain is a chain which consists solely of nodes which are labeled A, and I will speak about maximal A chain, and this simply means that we cannot extend it to, well, below, or we cannot extend it up, or we cannot extend it down. And since those chains are, well, they work exactly like letters and as words. Okay, so they take one argument. So I will usually write them in the concatenation style. So just instead of saying A on B on A on B on the argument, many closing brackets, 1, 2, 3, 4, 1, 2, 3, 4, I will just write A B A B. And since we know that this is a unary symbol, then we can treat it as a well-defined term. Okay, so those are for the patterns of RET1, and the only remaining pattern is called FIC, and the name is not really telling what it is. So the idea is that this is a pattern which consists of, well, one node, the root node is labeled by F, and the if child is labeled by C. This is a constant, and all other children I labeled with arguments. So this is I1, well, dot 1, dot 2, maybe dot I minus 1, dot I plus 1, up to, well, dot RET on F. We always assume that this I is well defined, so that I is smaller or equal than RET of F. Okay, but although this doesn't really, I mean, we'll not exploit it, but whenever we use it, it means that this is well defined. Okay, so this pattern has two letters, one letter, second letter, and all other, well, nodes labeled with elements of sigma of the signature, and all other are parameters. And we will compress those patterns. So there will be 3 separate operations, one for each type of pattern. So for A chain compression means to replace each maximal A chain A to L. So A to L means, as in a string notation, L nodes of A. Well, with a new symbol, with AL, this is a unary symbol. We define it on patterns, and later on, such a replacement is defined for patterns, and later on we explain how to do it for trees. So for instance, if we have F on A, A, C. Here it goes to F on A, C, and here again A, C. Then when we replace it, then we get F on here it is A3 on C, and here it is A2 on C and C. Okay, if there was some other argument somewhere here, okay, let's say this is again A23, A, C, then again there is A3 applied on C. Okay, so we compress them all them in parallel, and moreover, we take only maximal chains. So technically, a single A is also a maximal chain, but there is no point in replacing a single A again with a single letter, so we just leave it be as it were. Although, if you want to prefer that, if you think that we use A1, then fine, but it's not really needed. What's important here is that I'm using this 3 to say that there were 3 letters A compressed, but this is just a notation convention. Okay, so the algorithm or whatever, the algorithm is replacing it just with new letters. It doesn't really store any information that this was from the letter A and there were 3 different A's used in this subpattern. Just the fact that those are different new letters which are not used in the term and different for different lengths. Okay, so that A2 has to be different than A3 so that nothing is really spoiled. Okay, for AB compression, what we do is we replace every subpattern AB with a new subpattern. We need some, well, just a single node, let's say D. Okay, so if there is a F on A, B, A, B, A, B, C, there's C here, then we change this term into F on D, D, C, and this is also D, C. And since A is different than B, which is always assumed, then this is well defined so that those occurrences of subpatterns do not overlap. So we always know what should be done so that, well, which one to replace and which not. Okay, so there's no ambiguity which one to replace. So for FIC compression, which is the last one, so what happens is that if we have some, let's say F2C compression, then it has to be that then we are replacing this pattern by just deleting the symbol and changing the label appropriately. So we will change this one into F, let's say F prime, and there are less children. So if those were 1, 2, 3, 4, then the order is the same. 1, 2, 3, 4. Okay, so maybe F for 4 children is not the best one, but let's say that we want to compress F1 C, and the pattern looks like this, that this is C, this is F on C, F on C, C. Then this subpattern occurs here, and it occurs here. So after decompression, we would get F prime on F prime on F prime on C. Okay, so the in particular, the arity of this letter F is 1 smaller than the arity of F. Okay, and this observation is somehow important because our algorithm will depend on the maximal arity of symbols in the signature. So what's important is that when we make, if the maximal degree of the nodes in some term is K, and we perform some compression, then the maximal degree is still at most K. Okay, and this is easy because for unary, well, for those A chains, then we have nodes of arity1 and they are turned into nodes of arity1. The same for AB, we have nodes of arity1 which are turned into nodes of arity1. And for this FIC, we actually turn RET, well, some K prime into K prime minus 1 because we remove one of the children. Okay, so we do not increase the arity of the letters in the signature. We extend the signature by the new letters, but the maximal arity of those letters does not increase. It could decrease in principle. Okay, so this is now the so this is something which I assume that will be known. But since there are some new faces, then we'll have some algorithm which is non-deterministic. Okay, so it makes some non-deterministic choices, and we want to show the correctness of this algorithm. So there are two properties of the non-deterministic algorithm which we need to ensure. First is that it is sound, means that when restricted to context unification, that if some equation has a solution, sorry, it doesn't have a solution, does not have a solution, not have a solution, well, then for any non-deterministic choices, the new equation u prime equals v prime also does not have a solution. Okay, so in essence, whatever we do, we cannot turn an unsatisfiable equation into a satisfiable one. Okay, it could be the other way around. So if we made some bad decision and the equation had a solution, but we made some bad choice, and then the new equation doesn't have one. This is fine. We cannot turn a negative instance into a positive instance. Okay, and the second property is completeness. So that the algorithm is complete, meaning that if the equation has a solution, then for some choices, some non-deterministic choices, well, the new equation u prime equals v prime also has a solution. Okay, so the first one means that we do not spoil the things by just creating some false solutions, and the second means that if we have a solution, then for some choices we are able to keep it, so we can just proceed with the algorithm and make everything work. Okay, I think it's more or less time for a break, so maybe it will be good time for a break. Are there any questions concerning the part that we have so far discussed?
Well, so far I even could understand what is happening. That's, I think. Well, but after all, just well, it was really, and well, what you said so far, it was really, once you know the first part and once you know what you did here, it's clear. Of course, inventing it must have been, well, really something amazing. How did you come up with the idea to try to solve this problem using the method for strings?
So the idea that that somehow the algorithm for strings should generalize to context unification. So this was from the very beginning. Everybody thought that this should be decidable, and you should generalize the algorithm for strings. The problem is that
you mean it was thought that you should generalize just any algorithm for solving word equations,
yes,
or
that
just your particular algorithm?
No, that some algorithm for word equations should eventually generalize to this setting.
I see.
But you couldn't really do it. Well, maybe it's possible, but people failed with trying to do it with Makanin's algorithm and with Landowski's algorithm. For some reasons. Okay, mainly because they have some heavy string combinatorics component, which is not so easy to generalize to.
Yes, right.
But actually, if you try, so I didn't try solve it in the first attempt. In particular, if you try it to somehow encode it in the word equations and solve it through word equations, then it's not so clear whether you can do it or not. So you really need to generalize the method appropriately so that has some, well, you really have to. This was possible with generalization of the whole approach, meaning that you want to make some compressions, but if you just try to encode it inside the word equations, then it does not seem to be solvable then.
Yes.
Because
Oh,
essentially
yes, right.
it uses, in some sense, it uses some context-free constraints because the terms need to be well formed.
Yes.
So just for the brackets, you need the context-free constraints which cannot be supported. Maybe some subclass can be supported, but then it's not so easy with how to deal with that.
Oh yes, if there were such a reduction, then this, in order to show the decidability, this algorithm wouldn't be needed after all. You would need only the algorithm for word
maybe some
equations.
combination of reduction and some improvements of the algorithm would work. So, I mean, you could have some very specific constraints. So it could be that you could solve them with some algorithms and not with some other. So
yes, yes.
I wouldn't like to go into the details, but there are some extensions of the algorithms for the word equations that for some combinations of the extensions, some of the algorithms do not work for some reason.
Yes.
Like you could also describe the set of all solutions, and this work for Plandowski. You could also describe the set of all solutions for when you allow involution. You could allow the regular constraints, but if you allow regular constraints and the involution, that something breaks down and you cannot describe all the solutions. So
yes. Well, so we are about, I think it's about time to continue. And yes, unfortunately, I will have to leave about 5 minutes before the end. Just, well, because I have to run to a different place. But I will be here almost all the time, almost until the end, yes.
okay, so I'll try to finish 5 minutes before.
Well, if you can, I would be
Instead of
grateful.
5
Yes.
minutes later, as usual.
Yes.
Okay, so I think it's time to resume. Okay, so essentially soundness, if you reverse this condition, it says that if something does not have a solution, then afterwards it should not have a solution as well. If you reverse it, then it means that if afterwards it has a solution, then before it also had a solution, which means that essentially whatever you do on the equation, it is sound. So if you replace some variable, which could be a term variable or a context variable, you just replace it with t, with some pattern applied on this variable. So say you replace x with f on ax, then this is sound, because if you have a solution here, well, which substitutes x with some term t prime, then here you would need to substitute it with f on at, and everything works. And the similar for the patterns. Moreover, we could somehow replace it down. So we could here we pop some letters up. We could also pop them down in the sense that we have a term variable and we replace it with a term variable which takes with a term variable which it's applied on f, and this f has a lot of smaller variable x1, x2, one argument somewhere, and x3, x4, so that we do not know what's the, well, we do not replace it with a whole subterm, but some subterm with some variables. Okay, and again here, if we have a solution here, then we can just look at this whole term, what's defined together with those new variables, and use it as a substitution for x before. Or if we have we could replace the variable by a pattern, or a term variable by a term, or a pattern variable by a pattern, and then if the new equation is satisfiable, then previously we should have just used this pattern or term for the substitution for this variable. Okay, and we can also make some sub-pattern compression on those terms. So we could replace, say a pair AB by a new letter A prime. And if this new equation has a solution, then whenever there exists an A prime in a substitution for the variable, then in the original equation, we would replace this A prime back with AB. So in the whole substitution for both sides, we would replace every such a prime either because it's from the variable or from explicitly in the equation, and then this would also be sound. Okay, so essentially whatever we do on the equation, this is sound. We can from the new solution we can get the original solution. Okay, so now how to make those compressions. So in some cases making those compressions of subpatterns is easy, and sometimes it's not, and now we are going to define when it's easy and when it's not. So I will say that a subpattern, which could be also a term, okay, so we have given an equation, we are giving a concrete substitution. Usually it will be a solution, but we think just that it's a substitution. So we will say that an occurrence of subpattern in this whole solution term, which is obtained after the substitution on one side of the equation, it could be explicit, which means that all the letters, all the subterm was already, except for the perhaps for those parameters, was already present in the equation. So all the letter that it used are already in the equation. It's implicit if all those letters come from a substitution for a variable, which could be a term variable or a context variable, and it is crossing in the remaining case, meaning that some of those letters come from a substitution for a variable, and some of those letters come from the equation or for a substitution for a different variable. Okay, so maybe as an example, if we have f on x on c, and this x is f on a and the argument, then the whole term that so this requires two arguments. Okay, so this is c, so as f is binary, so the whole term that we get here is f on a on c, and then this one is explicit because it was in the equation, it was here. This one is also explicit because it was here. This one is implicit because it was here. This f is also implicit because it comes from a substitution for the variable. This f is explicit because it was in the equation. Okay, this af is also implicit, so this is a subpattern f a dot because it's fully in the substitution for the variable. Okay, this dot is somewhere outside, but we are looking only on the part which uses the letters, so this is a implicit. But for instance, this ff is crossing because one of those comes from x and the other one comes from outside of this x, so here from the equation, but in principle it could be from a different instance of some other variable. Okay, so that one is crossing. And we are focusing on those subpatterns that we are defining previously. So either for pairs, for chains of this letter of those FIC patterns. And I will say that this is a crossing pair for some fixed solution if it has at least one crossing occurrence. Okay, crossing occurrence of the subpattern. This is a crossing A if it has at least one crossing occurrence of an A chain subpattern, and this is again a crossing Favre-Leaf subpattern or FIC subpattern if it has at least one crossing occurrence. Okay, so those crossing occurrences are those which are problematic. So something is crossing if it has at least one such a bad occurrence. If all of those are non-crossing, then this is a non-crossing pair, non-crossing A or non-crossing chain, and a non-crossing Favre-Leaf subpattern. Okay, and so our sub-procedure will simply compress the patterns which it can see in the equation. So for instance, if we have an equation f on c on x on c, then if we want to make the compression f to c, then it will only replace this one in the equation. Okay, so this is the pattern sub-compression, and I will sometimes say that there are different variants for different types of sub-patterns. So there is a sub-pattern, Favre-Leaf compression or pair compression or blocks or chains compression, but also use just the general term subpattern compression to denote that, well, the subpattern is somehow a parameter. Okay, they work somehow differently because they replace different subpatterns. But one name, I will just use one name to conveniently state all the lemmata. But remember that for A chains, we replace all occurrences of all subpatterns in parallel. Okay, so if there is F on A and here it is A, then both of those are replaced in the same run of the subpattern compression. Okay, and for FIC we replace for a fixed child and a well, fixed child number and fixed variable. Okay, and this procedure is sound. Sorry, excuse me. This is easy because it just replaces some subpatterns by different letters, and we know already that this is sound. And moreover, if what it compresses is non-crossing, then it's also complete. Okay, so if AB is a non-crossing pair with respect to this solution, then it is complete with respect to this solution. Moreover, if A has no crossing chains with respect to a solution, then this then compression of A chains is complete, and if FIC is non-crossing, then it is then when performing this subpattern compression is complete. Okay, to be more precise, what we actually claim is that our procedure, after the replacing of this subpattern, we get a new equation which has a corresponding solution, such that if we look at this new solution applied to the new term, then this is just the old solution applied to the old term, on which we perform the appropriate compression. So the AB pair compression or A compression or FIC compression. And the reason why it is so, why it is complete, is that imagine that we perform, let's say, AB pair compression, AB compression. So we look at this S on U, and we look for every possible occurrence of this AB. And the new substitution is defined such that this substitution of X, this is S on X with AB replaced by C. So just we perform as a mental experiment this compression on the substitution for the variable. Okay, so when we look at this S on U and we look at each occurrence of this AB, so what can happen is that this occurrence is explicit, then the algorithm replaces it. It could be that it is implicit, so S prime replaces it. Okay, implicit means that it comes fully from a substitution for a variable. So this new subprocedure S prime, it will replace this occurrence because it replaces each occurrence in the substitution for the variable. And the last case is that it is crossing. But no, this is not crossing because we assume that this AB is non-crossing, so it doesn't have any crossing occurrence. Okay, so every occurrence which is there of AB, which is in this solution applied to U, will be replaced by this new letter. Okay, so the S prime on U prime is obtained by replacing every possible AB with this new letter C. So the same applies to S on V. So they are S on U and S on V are equal. So also those two are equal. So we have a new solution, and we know how this looks after the solution, after applying this substitution, and it's still equal. So this is a solution. Okay, and the argument for all other types of compression is the same. This doesn't really depend on what we compress, is just on the fact that each type of that we assume that that there are no crossing occurrences, which means that each one is either explicit or implicit. Okay, so we could perform those subpattern compressions when something is non-crossing, but the problem is that usually something is crossing. So what we want to do is to uncross it. So to take our instance, assume that there is a solution, and if there is a solution, so change this instance so that there is a corresponding solution for which this thing that we want to compress is non-crossing. Okay, so let us look at the most, let's say, involved case of this FIC, and we assume it's crossing for some substitution S. So what does it mean? So it means that there is some occurrence of this subpattern FIC, which it spreads somehow between the variable and something outside of this variable. So it could be that in the equation there is f and it's applied on some variable x. Oh, okay, I've written y. So applied on some variable y such that s on y is equal to c. Okay, the other option is that there is some variable x which is applied on c, and what happens is that s on x is equal something, and this the node above the well, it has the unique parameter on which we apply c, and this unique node on top of this well, the father of this parameter is f, and this is the if child. Okay, and the last option is a combination of those two, so it could also be that we have xy, and this f has this f above the parameter and the if child, and the parameter is the if child, and the variable on which we apply it is y, such that the solution of y is c. Okay, and in each of those cases, it's easy how to say what should we do. So if there is f applied on y and the solution for y is c, then we just replace y with c. It's one letter anyway. So then this is f with explicit, and the c becomes explicit. So explicit, it's given explicitly in the equation. So now it's no longer crossing. And of course we need to guess it. So we need to guess that this is indeed crossing, and we need to uncross it. Okay, in the second variant, we have there is x which is applied on c, and then we need to, well, push out, so pop down this letter which is on top of c. So we have a c, there will be f, and there is x which is applied on this f. But the thing is that there could be also some other children of f. So if f is a unary node, then that's it. But there could be also some other children of f. And in principle, we do not know what they are. So we could try to guess those terms, but they are not bounded by, there's no reason why they should be of some bounded size or anything else. So there are some arbitrary terms. So we just introduce new variables for that. Okay, so those are fresh variables. Which is a little bad thing, because we have just introduced fresh variables, which is always a problem, because then someone needs to bound the amount. Okay, but nevertheless, it works. So we introduce some fresh variables, and if it is x on y, then we do both things. So on one hand, we replace y with c, and on the other hand, we pop down those. In this case, I will call this popping up. So for y, this is pop up, because we are somehow popping a letter up the term, and this is popping down, because in a sense we are popping down the letters from x, and here we do both, so we pop up and pop down. Okay, and it's easy to see, well, that afterwards this is non-crossing. It requires some case inspection perhaps, but for appropriate choices, it is non-crossing. Okay, we can write it as an algorithm just for the sake of it. For some reason, I also wrote this one, but maybe it's not important. Okay, so just for consistency, if some of those fresh variables is also c, then we also replace them, just to be consistent. So there's no variable which uses c. Okay, this is a code, but hopefully it's the same. There are some margin cases, like if the substitution for the variable is empty. So if this f here was the only letter and now x just returns its argument, then we should remove this x, and this is again done by non-deterministic. Every decision here is done by the non-deterministic guess. So whether the substitution for the term variable is c, whether indeed we should pop down from this x, this is a non-deterministic guess. and whether this X is empty, then again, this is non-deterministic guess, and whether those new variables are also C's, then this is still a non-deterministic guess. Okay, and the lemma it is that, first of all, this subprocedure is sound. I have it, okay. And this is clear, well, clear because, well, there was this lemma that a lot of simple subprocedures are sound, and every step that we do here is sound. Moreover, a composition of sound operations is sound, so everything is sound. This is the easy part. But what's important is that it is complete, in the sense that if we have a solution, if our equation has a solution, then if we make appropriate non-deterministic guesses, then afterwards this FIC is non-crossing with respect to the new solution. Moreover, those the terms defined by those two solutions are exactly the same. And this should be intuitively clear. So when it could not happen, so as previously, it means that there is one of those situations. Either there is X applied on C, or there is F applied on some small variable, or like that. But in each of those cases, well, we considered already X, small y, and we didn't do. We can check whether we changed them. So here, if we made the popping on X, then it cannot be applied on the variable because it's applied on this different node F. So we didn't pop the F, which means that F is not the last letter, so the letter above this extra node. So here the node is not, well, the thing above this, the parameter is not F, so we know that this is fine, or it is F, but the argument is not, so C is not the ith argument. So here, since we did not replace Y with C, then it means that it cannot be that the substitution for Y is C, assuming that we made the appropriate non-deterministic guesses. And here it is, again, the same argument. So either the variable, the value of the variable is not C, or the node above the parameter is not F, or the parameter is not on the if position. Okay, so just some simple case inspection. And of course, the value of the substitution is defined appropriately. So if the term for X, if the substitution for X was some pattern P applied on F on terms T1, there's the argument T2, and so on, then the substitution for the new X is simply P, and the substitution for the new variables are as defined here. So for X1, this is T1, and for substitution for X2 is T2, and so on. So the substitutions are consistent with what they were before. So those are primes. Okay, for uncrossing of AB, the argument is similar, just that there are no extra variables, because what does it mean that this AB is crossing? Again, either there is X which is applied on B, and the last letter here is A, so the letter above the so I will call the letter which is above this parameter node the last letter, and the last letter is A, or there is A and the B, and the root node here is B, or there is X, Y, and here the last letter is A and the root letter is B. So in this case, we just pop down the A, so we replace X with XA. There are no fresh variables because A is unary, so it has only one argument. Here we replace Y with by, and here we replace X with Xi and Y with by. Okay, and the same argument works. So this operation is sound, and if we make appropriate non-deterministic guesses, then it's complete, and moreover, we have a corresponding solution afterwards such that the AB is no longer crossing. For uncrossing chains, the only difference is that for X, it could be that, well, X could be something like there is A applied on X, and the substitution for X could be that there is a lot of A's applied on top. So just popping one letter is not enough. So instead, we replace X with A to LX, where this A to L is the, well, maximal. So we need to remove all of those letters at once, and the same in the other direction. So if there are A is the last letter, then we remove all this suffix. So the maximal chain of those letters A above the parameter node. Okay, and the argument for each of those operations is similar, so all of them are sound, and moreover they are complete in the sense that it was already said for each one of them separately. They are complete in the sense that if we make appropriate non-deterministic guesses, then we get an equation which also has a solution, and moreover the corresponding terms for the solution for the previous equation for the new equation are the same, and this subpattern is no longer crossing. I was saying a subpattern, although this means that all of the A chains are patterns, but just for the short of the notation, the subpatterns are, well, the P is non-crossing. And this is shown exactly for each one of them as before. Okay, so the whole algorithm, this simple, this does not. And the whole algorithm now simply chooses some term and compresses it. Okay, this is of course again done in a non-deterministic fashion. So what we do is that we choose a subpattern. So while the sides of the equation are non-trivial means that they are, let's say, not of size 1. If they are of size 1, then both of them are of size 1, then this is true. This could be trivially solved. So we choose some subpatterns, and subpattern depends on the letters. So the letters are sigma. So from the alpha, this is the trim signature. So from the equation or some fixed F, A, C. So there are some 3 fixed symbols, let's say, from the initial signature, which we can use. So from the trim signature, and then we choose this subpattern, so either the FIC or the A chains or the per AB, and we make the compression. So we make a non-deterministic guess whether it's crossing or not. If it's crossing, then we uncross it, then we make the appropriate popping, and then we make the compression. Okay, and we, of course, we need those new letters in the signature, but then they could be removed by the trimming. And this similar action is done for the AB compression and for this FIC compression. So if we make the non-deterministic guess whether it's crossing or not. If it's crossing, then we make the appropriate uncrossing, and afterwards we make the pattern compression. Okay, so it's sound. So this what I will show later on is that this procedure uses a quadratic space essentially, so n squared times k squared, where the k is the maximal arity of the input. And if the equation is not satisfiable, then it will never return yes. So it's sound, it will never terminate. And if it's satisfiable, then at some point for appropriate choices, it will return the answer, and all the time it will not exceed this quadratic space. Okay, so I will show that in some of the computation, it will not exceed this space, meaning that otherwise we can have a counter and just reject if we exceed this space. So we will so this modified version will never exceed this n square k square space. Okay, so there is a small side note that we are popping from time to time this A to L, A to R, those chains from the X, and it could be shown that even if some logic that this L and R, that there's always a solution such that those two are at most exponential. So this is not a trivial fact, and it needs to be shown, but it's known, and we will be using that, which means that if they could be at most exponential, then when we guess what's the length, it's at most exponential, so we can store it in polynomial space, and only afterwards we compress it. Okay, so this extra space for those lengths is at most polynomial. So now this extra problem that occurs is that initially we have some variables, but afterwards we introduce new variables due to uncrossing of those FIC patterns. And we somehow need to show that, well, the aim now is to show that there are not too many of them. Okay, so we will tie this variable, so such a new variable to the context variable which it introduced, and I will say that a term variable is owned by the context variable which introduced it. Okay, moreover, the variable is disowned, meaning that when its context variable is removed from the equation. Okay, so, and the claim is that at each time during the run of the algorithm, each variable owns at most k-1 term variables. They are the same for every occurrence of this variable. And the maximal number of those owned and disowned variables is, well, n times k-1, where n1 meaning the number of term variables that we have. Okay, and why it is that? So maybe without readings, so just a small notation that I will say that if we have x applied on some term t, then this x dominates, well, everything inside this term t. So domination means that it is somewhere higher in the tree. So now, by simple induction, we can show that if we have different occurrences of the term of this context variable, then when it owns some variables, then those variables are always dominated. Dominates owned variables. And why it is so? Well, at the very beginning, how we introduce the term variables, we replace x with x on f, and all those owned variables are somewhere below. Okay? But then there is no way to actually move this variable up. So what we do, we compress, we pop some letters from the variables, but this doesn't change the order on the context variable and this term variable. So it's those owned variables are always below. And also each occurrence of this x owns exactly the same set of term variables. Well, because when we remove term variables, we remove all the instances at the same time. So there is a fixed mode. If we remove x1, then we remove all of those occurrences. Okay, so if x owns some variables, then those sets are the same for every occurrence of x. Okay, which means that in a sense every occurrence of x owns the same variables, and all of them are below x. Okay, so now, sorry. So now, imagine that we introduce at some point the new variables. Okay, so there is f, which is x applied on f, and there are some term variables here. Okay, and at somewhere later, we again introduce new variables. But we introduce new variables in two cases. Either this x is applied on c, or this x is applied on some variable, and this is exactly on this variable, and the substitution for this variable is again c. Okay, but we know that all of those variables which were here, they are dominated by this x, so they are below this x. So if we are at this moment and this x is applied, well, not this x, some x is applied on c, then it still should dominate all of those variables from x1 up to x3. But it doesn't dominate any variables because there are no variables. Okay, so all of those variables but they were all removed somewhere before. And the same here, if x is applied on a single variable, then it dominates exactly one variable. So all those previous variables were removed earlier. Okay, and during the uncrossing, we will remove this variable and introduce some other ones. So this x no longer owns this context variable x no longer owns this term variable small x, because this owns the new ones. Okay, so when we introduce the new term variables that are owned, all previous ones, they needed to be removed somewhere on the way, which means that with one x we can associate at most k-1 term variables that are owned. Okay, moreover, when we remove some term variables, then all of those some context variable, then we remove all those all its occurrences at the same time. So all of its owned term variables get disowned at the same time, which means that indeed we have at most n times k-1 owned term variables. Okay, so as a result, we know what's the number of variables during the run of the algorithm. So there are at most n term variables, and at most m times k, context variables, and at most n times k term variables. So we can estimate how many crossing subpatterns are there in the equation, because each crossing subpattern, it requires some occurrence of the variable. Either it's somewhere on, well, at least one letter up. It needs the root of the variable, or it needs the bottom node of the variable. So the estimations need to be done somehow better. But what's important is that this is O of nk. So the proof that I'm giving here actually shows something like 2nk plus something. But if we make it very precise, the estimation very precise, some distinguishing how many exactly the variables were in the original equation, and we can show that something around nk different crossing subpatterns. Okay. At the same time, when we uncross some subpattern, then we introduce at most n times 2k plus 1 letters, because what could happen is that we replace every term variable by a letter, and we pop one letter up from a context variable, one letter up, one letter down. So we introduce two letters per context variable, one letter per term variable, but actually we could cancel the, well, we could also replace those new term variables, so those are counted twice. So if the estimations are made very precise, then we can show that this is something like 2 times n times 2k plus 1 term variables. Okay, I'm getting slightly ahead of my time is running out, and there are like, I need at least 5 minutes. So maybe it would be a better thing to just give the final argument on the next lecture, because I need at least 10 minutes to give it somehow in a reasonable way. I think Alexander is already out, so he cannot give his permission to do that.
Well, I'm still here, but I'm just about to run
wait,
away.
I have 10 minutes. 10 minutes, great. Sorry, I 10 minutes is fine. Okay, so there is one thing that we need to discuss. So when we know that if we have a solution and our algorithm makes it properly, then after uncrossing and the compression, we have some new solution. We get a new equation with new solution, which is smaller. Okay, but it uses some extra letters, which then could be removed because of the trimming. And this trimming has this bad property that it replaces some of the letters with some larger subterms. So it could be that we have a small, after the compression, we get a smaller term, but due to the trimming, we will get a larger one. Okay, which in principle is possible. But if we define our, well, not just look at the size of the term, but on the appropriate weight, then it could be done, then it's still fine. Okay, so the weight of the solution is just a number of nodes of arity 1 and 0 in the substitution. Okay, and for this measure, this trimming does not increase the weight. So we have some solution. Due to compression, we get a smaller solution, but then we move to the trimming, which could make the solution smaller. But if we look at the weight, then the compression decreases the weight, because either it removes a child on it, or it changes some, or it compresses several unary letters into a single one. So the weight will get smaller due to the compression, and then the trimming will not increase the weight. And why it is so? Because in the trimming we either replace a unary letter, we could replace it with a different unary letter, which is fine. Or if we have some node of some large arity, then we could replace it with our fixed node of with our fixed binary node and just binarize this tree. But here the number of nodes of arity 1 clearly does not change. But also if there are some leaves here, then again we have exactly the same number of leaves after the binarization. Okay, so the number of inner nodes somehow increased, but the number of letters is, but the number of leaves is still the same. Okay, so even if we change the solution because we trim the signature, then we are safe, because we no longer this doesn't spoil the fact that our solution is getting smaller. Okay, it just gets smaller due to a different measure. Okay, so the last thing that needs to be shown is that if there is an how the algorithm works. So if there is some non-crossing pattern, then of course we choose to compress it, because on one hand it decreases the solution size, and on the other hand it decreases the equation because it replaces something in the equation. Okay, so this is fine. But what could the bad thing is that if we make the uncrossing, that we make the equation larger, which is bad, because then it could the space in principle could be unbounded. But what we will show is that if the equation is large enough, so if it has at least some quadratic number of letters, then there is some pattern such that if we compress it, then we get less letters. So that if we choose appropriate pattern, then we have an equation which is smaller. So as our initial equation is just of linear size, it has n nodes. This means that we are all the time, we can choose the pattern to compress so that we are still all the time below this 48 n square k square. Okay, maybe I will not be able to show exactly the 48 because this requires some careful calculation, but let's say some big enough constant in front of this n square k square. Okay, and how to do that? So the argument is that if there are many constants, so imagine that we have many constants in the solution. Okay, so we look at S on U and there are many constants. Many means at least n squared times 2k plus 1 plus k plus 1. Okay, at least this number of constants. So we know that there are at most n times k plus 1 different crossing patterns. Okay, and there are no, and every occurrence of the constant is in some occurrence of crossing patterns, because we assume that there are no non-crossing patterns. Okay, so there is a non-crossing pattern, a crossing pattern which has at least, well, n 2k plus 1 k plus 1 divided by this k plus 1 k plus 1 occurrences. Okay, so some pattern has a larger number than this occurrences, and this is of course equal to n, and this is n times 2k plus 1, so at least this number of occurrences. But then this means that this compression removes, well, larger number than n times 2k plus 1 letters from the equation. But at the same time, the uncrossing, it introduces at most n times 2k plus 1 letters to the equation, which means that if we choose this pattern, then the equation gets smaller because we remove at least, well, this number of letters, and we introduce at most this number of letters, so the equation gets smaller. Okay, and the same argument holds afterwards. So if there are less letters, okay, so what remains is that the number of constants is at most n times 2k plus 1 k plus 1. So now we estimate the number of unary nodes. Okay. So wait. Okay, so all the remaining letters in the equation are the unary nodes. Sorry, I'm falsch. Not sorry. Okay, so this is the maximal number of constants. So if you look at the equation, then the number of symbols of arity 0 is this times n plus k minus 1 sorry, n plus k. So this is the number of term variables. Okay, so the number of, so this is the bound on the number of, on the symbols of arity 0. So this is also the bound on, bound on symbols of arity 2. Okay, so we know what's the bound on symbols of arity 2. So the remaining nodes, are unary. So there is some number of unary nodes. So since we assume that there are at least 48 n square unary nodes in total, then there is some bound, let's say 30 n square k square unary nodes. Okay, so there are some chains of unary nodes at various places. Okay, so now it remains to estimate how many chains are there. And this again can be estimated because if we look at the chains, so the node which is above the node which is above a chain has to be a node of arity at least 2. So this bound which is here, it says how many different chains are there. Okay, so now we are looking at each chain, and for each such a chain, an argument which was given for the word equations could show that if we choose the, okay, I will make it the appropriate estimation later on, but the same estimation as for the word equations shows that if we choose appropriately, then those chains are reduced by some constant fraction of size, more or less 1 over nk, which means that again, since we have a quadratic number of nodes in those chains, and we know that they will be reduced by something like 1 over nk because there are not too many crossing subpatterns, then we again remove some fraction of alpha nk nodes from the equation, and we introduce this single uncrossing introduces at most 2 times n times 2k plus 1 nodes. So again, we remove, we get a smaller equation. Okay, so those estimations need to be done precisely, but I ran out of time, so maybe I will just make it. I will comment it in 5 minutes tomorrow. Maybe make a slide to make it fast. Not tomorrow, on Monday. Maybe make a slide to make it faster. But the idea of this compilation is exactly as was on the previous slide for those FIC patterns. Here we just use the unary patterns for A and AB. Okay, I'm sorry that I ran out of time and that I made it slightly too long and for not giving the full argument. But in the end, to summarize, either there is something non-crossing which we can compress, and if there are only crossing ones, there are linearly many of them, the size of the equation is quadratic, so some of those, for one of those choices, we also remove a linear refraction, which will make the equation small enough to compensate for these extra letters that we get from the uncrossing. Okay, so that's what I wanted to say today.